Hello, my name is Roy Simpson. I'm an instructor of mathematics at Cosumnes River College in Sacramento, California. This is part B of a lecture on additional properties of lines. We've actually gone through the entire discussion of what a linear equation is and how to represent all of its solutions by using a graph. We've also done some applications, and we just finished a discussion about horizontal and vertical lines. In this lecture specifically, we're going to go ahead and continue and talk about parallel and perpendicular lines and do some more advanced problems concerning parallel and perpendicular lines. In this first example, we're going to go ahead and justify kind of a property of parallel lines by graphing a couple equations and noticing something about their graphs. The first equation we'll go ahead and graph is 4/5 y equals 4/5 x plus 2. I'm going to use the fact that we know from the slope-intercept form, y equals mx plus b, that 2 represents the y-intercept. So I'll just go ahead and plot that right here. And the 4/5 is the slope. So we'll go ahead and use the slope to get to another point. We're at the y-intercept of 2, use the slope by going up 1, 2, 3, 4, and over 1, 2, 3, 4, and 5. We'll go ahead and connect these dots here to get our graph, or the graph of the set of solutions to that equation. And then I'll choose another color for the second line here. The second line is y equals 4/5 x minus 2. Again, that negative 2 there, or minus 2, is our y-intercept. And we'll use the slope, which is 4/5, to find the next point on this purple line. So up 1, 2, 3, 4, and over 1, 2, 3, 4, 5. If I connect those 2 points, you should notice something kind of interesting about these 2 lines, that they are parallel. And you should also notice something in common with these lines: they actually have the same slope. So this is our theorem. Lines having the same slope are considered parallel. So the theorem reads that 2 lines are parallel if and only if they have the same slope. Okay. Working with perpendicular lines is not so easy. Actually, it's very difficult to show that the proof for the theorem that 2 lines are perpendicular, but we'll go ahead and try to justify it. The theorem reads as 2 lines are perpendicular if and only if their slopes are negative reciprocals. And that's kind of hard to understand if you just say it in language. So instead I'll just say, suppose you have the slope of one of your lines being m sub 1. So in other words, our first line has slope that. If the 2 lines are perpendicular, then the other one should have a slope of negative 1 over m sub 1. Whoops, I wrote an I there, but it's supposed to be a 1. Simple example, since we've seen an example of 2 lines that are parallel. Simple example of 2 lines that are perpendicular are these two. Y equals 3/2 x plus 4, and y equals, let's put a negative on that and flip that fraction, so a negative 2/3 x minus 7. Or it could be, it doesn't really matter what that last number is. What really matters is that this, the slope for the second equation, is not only the opposite in sign of the slope of the first equation, but it's also the reciprocal. Okay, so these are perpendicular. And there is a shorthand for writing perpendicular. I haven't seen it too much in a lot of textbooks lately, but it's like an upside down capital T. So if you do see that, some people use that as a shorthand for saying that 2 lines are perpendicular. Now, to show you kind of the property that I was just talking about, where the slopes of parallel lines are the same and the slopes of perpendicular lines are negative or opposite reciprocals, we're going to use an application here. This application can be had for free just by going to Wolfram demonstrations, or Googling Wolfram demonstrations. And I'm just using a free plugin, a free player And what I'm going to do is show you this one. The title of this is Slope and Equations of Lines Through Points. So I just typed that into Wolfram's search engine, and this came up, and I click on view line so I can see this line here, and I can manipulate this. I've shown this in a previous video, but what's interesting about this is that you can see the slope. It calculates the slope of the line, and it gives you the equation of the line. So you see the slope is a negative 3/4, and the equation is actually negative 3/4 x and then a positive 1/2. They have it written the opposite of what most mathematicians write it as in class, but actually this is a great form to have an equation of line in. So if I adjust either of these lines, you see those numbers adjust as well. So you see the slope adjusts and whatnot. But we'll leave it on something like this. Now let's go ahead and click on parallel line just to get a parallel line in there. Let me drag this line around. You can see this line is parallel, but also notice that the slope of that parallel line is a negative 2/5, just like the slope of our line is a negative 2/5. No matter where I drag this line, the slope is always a negative 2/5. It looked like it changed for a moment there. I don't know why. Oh, it's because the algorithm, I think, that they use to format the display. It's still a negative 2/5, but it's at the back end over there. Not a big deal. Anyhow, and also if I adjust the blue curve to change the slope to a negative 4/7, let's say, notice that the slope of the parallel line also is a negative 4/7. Okay. And a couple other things I should mention here. I've mentioned it already in a previous video, but I'd still like to mention it, that when your line is increasing from left to right, we call that a positive slope, and you can see that it is actually a positive slope. When your line is flat, like this, you have a zero slope, and you can see the parallel line also has a zero slope. And when your line is vertical, you have an undefined slope, and you can see right there the slope is undefined. Let me turn off the parallel line and turn on the perpendicular line. Let me move it out of the way too. And this coloring is difficult to read, but I'll read it out loud. The slope of our regular line, our blue line here, is a negative 3/8. And if you look at this green line here, the slope for that green line is a positive 8/3. So in other words, it's the opposite reciprocal of that. It doesn't matter how I move these lines, they'll stay in being perpendicular to one another, and it turns out that their slopes are negative reciprocals. Like this slope is 1/4, the blue slope is the slope of the blue line, and the opposite of that would be a negative, and then reciprocal would be 4. So a negative 4 should be the slope of the green line, and it does say negative 4x right there. Okay, so kind of neat. By the way, on this applet you can zoom out and zoom in and stuff like that. And you could also view the point slope form of the equation if you want to. Not a very handy form of the equation though. So we'll continue with an example here that's very typical in most intermediate algebra courses. Kind of a boring example, in fact. I'm not a big fan of the boring examples, but we'll go ahead and do it. Are the graphs of this equation and the other equation parallel, perpendicular, or neither? The only way you can actually tell is to figure out what the slopes of these equations are. And the best way to do that is to put these equations, both of them, into slope-intercept form, or in other words, solve for y. So that first equation, I'll just subtract 2x from both sides. And then I'll divide each item, or in other words, I'll divide both sides by 7. Dividing both sides by 7 is the same thing as saying I'm going to divide everything here, each term, by 7. It's actually a better way to say it anyway. So this equation, oops, I see that I wrote an x there. I meant to write a y. Okay. This equation becomes 1/7 minus 2/7 x. So y equals 1/7 minus 2/7 x. So I see the slope here, which is the coefficient on x. The slope is, for this first line, is a negative 2/7. Let's solve this second equation over here for y as well. I'm going to multiply both sides by 2. So I'll get, in other words, I'm going to multiply each item here by 2. So I get 2x minus 1 is equal to a negative 7y, and then I'll go ahead and divide each of the items, or each of the terms, by a negative 7. So I get y is equal to a negative 2 over 7x plus 1 over 7. And not only are these two lines parallel, they're parallel because the fact is that this slope of the second line here is negative 2/7 as well. So they have the same slope. So these are parallel. But not only are they parallel, actually this is a very trivial example. I didn't even realize I had this. They're not only parallel, but they're the same exact line. How do I know they're the same exact line? Well, look at the equation here. This is y equals negative 2/7 x plus 1/7. Over here, this is y equals a negative 2/7 x plus 1/7. They're the same line. But it doesn't matter whether the same line or not. You still go through the same process no matter what kind of problem is presented to you. If they're asking you if lines are parallel, perpendicular, or neither, if the slopes are the same, they're parallel. If they're opposite reciprocals, they're perpendicular. And if they're neither of those two things, which most equations are not parallel or perpendicular to each other. So if they're neither, you would just say they're not. They're neither parallel nor are they perpendicular. I get bored with those examples so quickly that I just do one and then move on. These examples are more interesting to me. Show that the triangle with vertices 0, 8, 6, 2, and negative 4, 4, show that that triangle is a right triangle. And remember, a right triangle is a triangle that has a right angle in it. Okay? So I want to show that these vertices form a right triangle. Well, let's go ahead and graph them very quickly. And because I'm graphing by hand, it's not going to be the best. I'll plot 0, 8. So I'll say that's 2, 4, 6, 8. So I'll pretend that that's point A. I'll plot 6, 2. So 2, 4, 6, and up 2. And I'll plot negative 4, 4. So negative 2, negative 4, and up 4. Now it doesn't look to me, just by visualizing or looking at this, it doesn't look like this will be a right triangle, but looks can be deceiving. If there's a candidate for a right angle anywhere, I'm going to say that the candidate might be here. That might be the right angle. Let me label these, by the way. This is point B and this is point C. So how do I use this information to find out if this is a right triangle? Well, a right triangle means that you have two legs that meet perpendicular to one another at a 90-degree angle. So we're hoping that these two lines are perpendicular. For those two lines to be perpendicular, the slope of the lines should be opposite reciprocals. So let's find the slope of the line connecting A and C. All right, so remember, here's A, here's C. So we'll take the difference in the y values. I'll go ahead and take A's y value first. So 8 minus C's y value, which is 4, over A's x value minus C's x value. And I get that the slope of the line segment AC is going to be 4 over positive 4, which is going to be 1. Now all I need to do is hope, cross my fingers and hope, that the slope from A to B is the opposite reciprocal. And if you think about the opposite of reciprocal of this one, it's going to be a negative 1 over 1, or just in other words, negative 1. Let's go ahead and do this. The point A, or actually the 2 points A and B here, the difference between the y values is 8 minus 2. Difference in the x values is 0 minus 6. So we get 6 over a negative 6, which cleans up to become negative 1. And it turns out that these two numbers are negative reciprocals, right? 1 is just 1 over 1. So if you tack a negative on that and flip it, it's still going to be negative 1 now. So this is definitely a right triangle. Now the last very typical style of example that you get in most intermediate algebra courses is this one, where you have to find an equation for a line that goes through some point they give you, and then is perpendicular to some other line or parallel to some line. So I just am using the same line here in both cases. So we have, I want the equation for a line that goes through this point 2 comma 7 and happens to be perpendicular to this line right here. So our first job is to find the slope of that line. So what we'll do is solve for y. Find out that y is a negative 3x plus 5. And to be perpendicular to this line, part A, to be perpendicular to that, we want the slope to be the opposite, which is positive, reciprocal. Well, the reciprocal of 3 is 1/3. So we want the slope to be a positive 1/3. Remember, the equation of a line is y equals mx plus b, at least the proper equation for a line. You could use point slope form, but I like slope intercept. And in our case, we are given that, or we just calculated that the slope for the perpendicular line is going to be 1/3. All we need to do now is find what that value of b is, and luckily they gave us a point. All you need is two things for the equation of a line. You need a slope and a point, or you need 2 points. As long as they give you two pieces of information, you have a line. So they gave us two pieces of information. They gave us basically a slope, 1/3, and a point that we could plug into this equation. We know that when x is 2, y is going to be 7. Great. So let me go ahead and solve this. I solved this kind of a weird way, where I see an equation, I have fractions, I'll just multiply everything by 3. A lot of people don't like that, but I don't mind. Because if I multiply each of these objects by 3, I'll get 3 times 7 is 21. 3 times 1/3, those cancel and I just have 2. And 3 times b is a positive 3b, which gives me an equation with no more fractions. It's just so I can avoid them. I'll subtract 2 from both sides to get 19 equals 3b. And finally, divide both sides by 3 to get 19/3. So the equation of the line that is perpendicular to this equation here and goes through the point 2 comma 7 is going to be y equals 1/3 x plus 19/3. That's the answer to part A. Part B, they're asking, well, what's the equation line that goes through that point but is parallel to this given line? So we want, for part B, we want the slope to be the same as negative 3. Again, standard form for a line is y equals mx plus b. Replace that m with our slope that we want it to be, a negative 3. And again, we're at this point where we are just missing the value of b, but that's pretty okay because I'm going to plug in the point that this line is supposed to go through. When x is 2, y is supposed to be 7. So I see that's negative 6 right there. I'll add 6 to both sides and find out that b is equal to 13. So the equation of the line that is parallel to this line right here but goes through this other point is going to be y equals a negative 3x plus 13.